I'll talk about some relationships between loop homology of some spaces arising in toric topology and in homotopy theory of polyhedral products, and some structural results about commutator subgroups of right-angle Coxeter groups, and more generally arbitrary graph product of groups. Well, there seems to be a very nice correspondence between these two series of results, and the unifying framework behind this is a theory of polyhedral products. And so I'll give you a couple of examples where you can translate some results on homotopy theory about the loop homology or the rational homotopy Lie algebras of some spaces on one hand, and right-angled Coxeter groups, their commutator subgroups, and more general graph products on the other side. And it seems to be there is much more to explore about this correspondence. So it's only the beginning of the journey, and then I invite you all to continue, as it seems to be very fascinating for myself as well. And this is this project is a joint work with several people. I try to list it here, most of them: Yelena Gerbich, Marina Ilyasova, George Simons, Steve Terrio, Yakov Verevkin, Jivu, and there are also others which I'll mention during my talk. Okay, so I'll briefly recall the definition of the polyhedral product just to set up the notation, because there are several competing notation for these spaces. So it's like we have a sequence of pair of spaces X, I, AI, which we denote the sequence by the boldface letters. And we have a finite simplicial complex on an ordered set M of M indices. We always assume that the empty set is a simplex. And then for each subset, we prepare a subproduct in the product of X's. So like in the usual way, we take the smaller set if I is not in this index set, and we take the bigger space if I is in the index set. And then we form this K polyhedral product of this sequence as a union of all those subproducts over all simplices in K. So it's like this union of those products, and it sits inside the big product of X, is the product of all X's. And we use a shortened notation, so when all the pairs are the same, we just do not use the plain letters instead of boldfaces. And when the smaller space is a point, we just use the notation X to the power K. It's like, it seems to be very convenient for myself. It's like a polyhedral power of a space or of a sequence of spaces. Well, most of you know many examples of this, but I'll give you some more in a second. But let me first review the sort of basic categorical approach to this. So you can look at that as some simple colimit of some very simple diagram. You look at the very small poset category of faces in your simplicial complex. So it has an object for every simplex, and morphisms are inclusions. So there is at most one morphism between two objects. And we have the big category of state topological spaces for start. And we look at the diagram, the functor from the small category to the big category, which takes a simplex to this product. Remember, this is like the product of X's and A's determined by I. And obviously, because everything is pointed, whenever you have a morphism, you also have an inclusion of the corresponding spaces here. So it's a functor, and then you can say that the polyhedral product is a colimit of this diagram. Or in a more simple way, you can say that it's like a nested union of all those products over all simplices in K. Well, I spent this little time to set this up in a categorical fashion because we are going to change the categories very soon. But this kind of formula will be kept. So, right, now let's go briefly through examples. Many of those examples you have already seen in the previous talks. The first one is you take the pair, the circle and the point, and then you get this subcomplex in the M torus, the polyhedral power of the circle. In the geometric group theory, it's often called the Salvati complex, corresponding to the right-angle arcing group, although, yeah, Salvati complex is defined for arbitrary arcing group, not just right-angled one. And for the right-angle arcing groups, it was known before. Probably the first paper where it appeared was the one of Kim and Drush in 1980s, where they just proved that this space is a K-pi1 space for the what they call partially commutative group, which is the same as a right-angle arcing group when K is a flag complex. So anyway, and nowadays we think of it as a polyhedral product. So it interpolates between the M-fold wedge and M-fold product of circles. So if K is a discrete complex, you get a wedge. When K is a full simplex, you get the product. And another important example is when K is just the boundary of simplex. If you have just only one subset missing, the whole set of M letters is missing, and all other sets are present in your simplicial complex, then you get what is called in topology the fat wedge. It's obtained from the torus by removing the top cell. Okay, and yeah, in general, this polyhedral power interpolates between M-fold wedge and M-fold product. Right, another important example is you take the pair real numbers and integers. Now this second space is not trivial, it's not a point. So you get something sitting inside Rm, inside the Euclidean space, and it's like it's formed of planes parallel to coordinate planes. So for instance, if K is disjoint of M disjoint point, then you get a grid consisting of all lines parallel to one of the coordinate axes. And again, when you have this boundary of this simplex, you have this infinite cubillage, like it's a union of all integer hyperplanes parallel to coordinate hyperplanes. It's like an infinite cubical complex. Right, so we denote it LK. Right, so another pair of important examples, when you take infinite dimensional real projective space, which is a classifying space for the Z2 cyclic group of two elements, and then you can form the corresponding polyhedral power, which sits inside this M-fold product of RP infinities, in the same way as we've seen for the torus, and similarly CP infinity to the power K. This space is often called the Davis-Januszkiewicz space because it's homotopy equivalent to the space considered in the work of Davis and Januszkiewicz, the equivariant, the Borel construction on the moment angle complex. Okay, so and now the final set of examples are the real and complex moment angle complexes. So you have the pair D1 as 0. So it's a segment and it's two boundary points. Then you have what we call the real moment angle complex, because there is no, I don't know of a better name. If you suggest a better name, I would be grateful. Yeah, it appears throughout all different papers on geometric group theory, like Mike Davis, Ruth Czerny, and all others. But I couldn't see a good name for that. So it's a cubic subcomplex in the M-dimensional cube. And it is a manifold. So, well again, if K is disjoint, it's one-dimensional skeleton of the cube. If K is a boundary of the simplex, it's just the boundary of the cube. And moreover, what is more important is like if you start with a triangulated sphere, like a boundary of a simplicial polytope, for instance, then you get a topological manifold, which is a very good feature of this space, which adds breadth in some geometry into all those constructions. And there is another version of this space where you replace D1 as 0 with D2 as 1. This is called the moment angle complex. It has lots of nice geometric structure, but this is a very different story. And well, it's forms of disks and tori. It's patches of disks and tori, and again, it's a topological manifold when you start with a sphere triangulation. So actually, this is a moment angle complex, and this one is its real version. That's what it's called. We call it real moment angle complex. But there are no angles here, unlike here. So maybe it's not a very good name, but I don't know a better one. Okay, so now what can we do with all that? Well, first of all, let's look at this construction of the polyhedral product as a generic categorical construction, and then try to change the categories. So what we can try to do, we can change spaces by groups, and then we arrive at another familiar construction in geometric group theory, which you can also do with topological groups, and this is kind of interesting as on its own. So you start with a sequence of groups. There can be topological groups or just discrete groups, whatever. Well, for some reasons, it's better to assume they are non-trivial. So that will save some space later. Then you don't have to put these assumptions in later statements. So a sequence of non-trivial topological groups or non-trivial groups. And then again, you can, for arbitrary subset, you can form a subproduct in the m-fold product of those groups. And yeah, so this is a subproduct. The groups are naturally pointed, so there is no problem with base points. And then you can say, look at the same sort of diagram, but now in the category of groups, you send a simplex in your simplicial complex K to the product of those groups, and then you take the colimit. But now the colimit is taken in the category of groups or in the category of topological groups rather than spaces, and that's a very different object. It uses like the coproduct is a free product, whereas in topological spaces, the coproduct is a wedge. But it's the same sort of formula, and it's called the graph product of groups. It's called graph product because it actually depends, although it's, as we wrote it, there is a simplicial complex in this notation, so that it universally fits with the previous constructions like polyhedral product, but it depends only on its one skeleton, on the graph, and therefore it's called the graph product. Because like the category of groups is not as rich from the homotopy theoretical point of view as a category of topological spaces. You cannot do homotopy with just groups. You can do with topological groups, but that's again kind of different story. So now, well, yeah, the graph product depends only on the graph of K. Namely, you can write it down with generators and relations, where by a very precise formula, so there is an isomorphism of groups. So you take the free product of all your groups and set up the commutativity relations whenever you have an edge in your simplicial complex. So when two vertices in your simplicial complex are joined by an edge, the corresponding elements in all the corresponding elements in your groups commute. So you can do this also with topological groups. You have to be a bit more careful. You have to look at the well-pointed topological groups, but this construction exists in the topological category as well. So you can see from this that it depends only on the graph, right? So you have to check the universal property of the colimit for this presentation to see that it actually agrees with the previous definition, but it's an exercise, it's not complicated. So, and as a corollary, you get that, I mean, it depends only on the graph. Therefore, it's called the graph product. Well, and then there is a natural question to ask how those two constructions are related. Namely, well, yeah, before I proceed to this, let's go through two very basic examples, which are familiar to all of you. Like the right angle arcing group is a graph product when all the groups in the vertices of the graph are just Z, infinite cyclic groups, as algebraists say, or groups of integers. And well, yeah, then you have the quotient of the free group. That's a free product of all those GIs by these commutativity relations. And well, and it like interpolates between the free group, which you obtain when you have discrete complex, and the free abelian group, which you get when you get a full simplex. And another example is a more geometric example is what's called right angle Coxeter group. So it's when you take Z mod 2 as a vertex groups, and then you have a quotient of the free group by the relations. You have one extra relation that the square of each element is 1. And here what you get is right-angledness, because many of those groups have geometric presentations as like reflection groups in like Euclidean or Lobachevsky, or in Lobachevsky space, hyperbolic space. And therefore they correspond to the case when you have the right angles between the reflecting hyperplanes, and therefore they're called right angle Coxeter groups. And this right angle in their arting groups, this word just came from this Coxeter setting. Okay, so these are two examples, but there are many more. Of course, you can form arbitrary graph products with other finite groups, like cyclic groups, for instance. And well, that is a natural question. How this graph product relates to the polyhedral product. Namely, you can form the graph product and then you classify it. Or you can classify each group and then take the polyhedral product. And when those two things agree. And of course, well, because this polyhedral product depends on the whole K, on the whole simplicial complex K, whereas this graph product depends only on its one skeleton, you cannot expect this to be held in general, to be true in general. And well, in order to see to what extent it holds and when it fails, it's convenient to look at this homotopy fibration. So you have this homotopy fibration of polyhedral products. So you classify each group in your sequence. This boldface G is a sequence of groups. You classify them and form the polyhedral product, and then you look at the universal spaces for those groups and take the group itself. That's another set of pairs. And then you can either do it by hand or use the functorial properties of the polyhedral product. You can see that there is such a homotopy fibration. For example, in all those examples we considered before, like you have this LK space, like infinite cubillage. It's a homotopy fiber, the homotopy fiber of the inclusion of this subcomplex in the torus included in the whole torus. That corresponds to the case G equals Z. All the vertex group are Z. Then this finite cubical complex, the real moment angle complex, is a homotopy fiber of the inclusion of the Rp infinity to the power K to the Rp infinity to the power M. That's an inclusion of CW subcomplexes, and that's its homotopy fiber. Well, here you have to classify S0. Well, so as the BS0, B0 2 is like Rp infinity, and instead of E, that's infinite dimensional sphere, but you can replace it by D1, just anything contractible. So that's a better model, it's a smaller one. And similarly with Cp infinity to the power K includes into the M-fold product of Cp infinity, as the fiber is this moment angle complex. That corresponds to the case G equals the circle. That's a topological group. All right, so these are all examples of this homotopy fibration. Then, well, there's this terminology of flag complexes. So the flag complex is basically the simplicial complex determined by its graph. You fill in all complete subgraphs by simplices. Or you can say a simplicial complex is flag whenever any set of vertices which are pairwise connected by edges spans a simplex. So and then we have this theorem with Nige-Ray and Fork that basically the classifying space of the graph product agrees with the polyhedral product of the classifying spaces if and only if K is a flag complex. And well, you need to prove that for flag complexes, and you need to see why it fails when K is not flag. And to see why it fails when K is not flagged, it's convenient to look at what's called high Whitehead products. Basically, that was something which exists in homotopy theory of spaces and does not exist in groups. Like in groups, whenever you have elements which are pairwise commute, then they commute in total. But in spaces, this is not quite the case. You can have all the versions of high commutativity. And therefore, in the homotopy groups of these polyhedral products, when K is not a flag complex, that's basically if and only if condition. When K is not flagged, then you have a high Whitehead product. For every missing phase, you have a high Whitehead product in this space. And this what abstracts this identity to be true in general. Well, this can be fixed by, you can define graph product using homotopy colimit rather than colimit. When you do polyhedral products, colimits and homotopy colimits agree. In the definition of the polyhedral product, you can replace colimit by homotopy colimit because the appropriate diagrams are already cofibrant, and therefore the homotopy colimit agrees with homotopy limit. But in groups, this is not the case. You can do homotopy colimits in the category of groups, but that's going to be a very complicated gadget. But this is what actually replaces the graph product if you want this to be true in general. Okay, so, well, now, yeah, when you restrict yourself to the case of topological, to the case of discrete groups, then you get from this kind of homotopy equivalence, you get something much more familiar. And well, I'll set it as a theorem, but it's actually like a folklore result. Different parts of it go back to like 30s to the work of Whitehead and so on aspherical spaces. And many parts of this, I collected here these facts, but many parts of this statement appeared in different works in geometric group theory from 50s. And well, so if you have a graph product of discrete groups, then there are several things you can say about the polyhedral product of their classifying spaces. First of all, for arbitrary K, the fundamental group of this polyhedral product is a graph product. That holds for arbitrary K. But then the asphericity holds if and only if K is flag. So higher homotopy groups vanish if and only if K is a flag complex. Then the higher homotopy groups of those two pairs, two polyhedral products agree. And the fundamental groups of this pair, remember we had all this fibration, this pair features in this homotopy fibration. So it's like like a fiber of these inclusions, right? So that's an important pair. So, and the fundamental group of this pair is isomorphic to the kernel of the canonical projection from the graph product to the Cartesian product. It's sometimes called the Cartesian subgroup of the graph product. So again, well, that asphericity statement, as I said, it's basically the Whitehead theorem, and he has a theorem on saying when you glue aspherical spaces along some recipe, when you get an aspherical space, a Whitehead theorem tells you when this is the case, and this follows from that. And to see that it is not flag, to see it's not aspherical when K is not flag, you have to look at this kind of higher Whitehead products. Yeah, well, I briefly covered it here, but it's like, yeah. So if K is not flag, then you can pick up like a subcomplex corresponding to this missing phase, the maximal non-phase, minimal non-phase. And the property of the polyhedral product tells you that it's actually a retract of the whole thing. So it's a fat wedge of those spaces, and it's a retract of the whole gadget. And the homotopy fiber of this inclusion is like this wedge of K-1 dimensional spheres, because if groups are discrete, so here, so these GIs are just discrete sets, and that this K-1 fold suspension is just a wedge of K-1 dimensional spheres. So you have a higher homotopy groups appearing here, and because it's a retract, you have this higher homotopy group appearing here, and therefore then those things are not aspherical. And the rest is like obvious, like the statement about the homotopy group of this space. That's the fundamental group is a Cartesian subgroup. The kernel follows from this homotopy exact sequence of this vibration. Okay, so yeah. Now, okay, specializing to the most well-known cases of the right-angle arcing groups and right-angle Coxeter groups, we get these two corollaries. Well, probably, yeah. So that's like this thing about this, what's called Salvati complex or Kim and Rouge complex. Like its fundamental group is a right-angle arcing group, and it's a spherical space if and only if K is flag. And now if you look at this gadget, this infinite cubical complex, then its fundamental group is isomorphic to the commutator subgroup of the right-angle arcing group. Because the Cartesian subgroup, when all the groups in the graph product are abelian, the kernel from the map of the graph product to the Cartesian product is just a commutator subgroup. So this is a commutator subgroup of the right angle Artin group. And similarly for the right angle Coxeter groups. But here you have a finite k/1 space. And yeah, and the fundamental group of this real moment angle complex is a commutator subgroup of the right angle Coxeter group. Okay, so by those, well, I am primarily interested in those two commutator subgroups. Well, first of all, they have a very, very nice geometrical meaning. Well, this can be illustrated by two examples. First of all, well, if K is just an M cycle, the boundary of an M-gon, then if you look at this real moment angle complex, then you can actually prove that it's an orientable surface of some particular genus, of this genus. So if you have like one, so a sphere, then a torus, then a surface of genus 5, surface of genus 17, and so on. That's what you get from the M-gons. Those surfaces are in a sense the most symmetric out of all Riemannian surfaces. They have the most possible commuting involutions acting on them, like local maxima of number of commuting involutions. The most symmetric Riemannian surfaces in a sense. Like the surface of genus 5 is more symmetric than a surface of genus 4 or a surface of genus 6. It has more commuting involutions. And well, this observation, well, all those kind of things are, you can find as a sort of ideas in the work of Coxeter of 1938. And so and the fundamental group of this one is the commutator subgroup of the right angle Coxeter group. So it's in this case, the commutator subgroup is a surface group. And now these are like boundaries of M-gons are like triangulation of one sphere. And if you look at the triangulation of two spheres, you get something which is much more kind of abundant. There are lots of polytopes in dimension 2 or in dimension 3, lots of simplicial polytopes, and for every simplicial polytope you get some three-dimensional manifold out of this construction of real moment angle complex. And the commutator subgroup of this right angle Coxeter groups is a three-manifold groups, and those manifolds are quite interesting. They, in many cases, they have kind of hyperbolic structure and so on. So you look at not just an abstract commutator subgroup in some subgroups, but you look at the fundamental groups of some manifolds with nice geometry by looking at this commutator subgroups. Okay, so well, now, yeah, now let's see how you can say something about these things, about this group. So, well, okay, let's study those commutator subgroups more closely. So we first consider the topological case, where all the groups are, that actually was where this our approach began. Yeah, we started from the toric point of view, from the toric topology, then we came to moment angle complexes and polyhedral products, and only after that we realized that there is some links to geometric group theory. So that's where our approach started, at least. So we look at these groups circles, right, and we have this homotopy fibration. From this moment angle, that's the moment angle complex, right? The one formed of disks and circles, and it's a homotopy fiber of the inclusion of the CP infinity to the power k to the product of m CP infinities. You have this homotopy fibration, and you can loop it. Consider the loop spaces, and then it splits after looping as a fibration of spaces because it has a section. So that as a loop space, the loop space on this Davis-Januszkiewicz space is that this polyhedral k power is a product of the loop space on this finite CW complex and the torus. However, this is not an H space splitting. This is not true as H spaces or as topological monoids, topological group. This is not the case. And the way to see that is to look at the Pontryagin algebras, loop homology. So if you look at the loop homology, then you see that the corresponding sequence of Hopf algebras, the loop homology algebra, doesn't split. You have a short exact sequence of loop homology algebras, but it doesn't split in general. What it looks like is you have this, like in the center, you have, in the middle, you have this loop homology of that complicated space, that CP infinity to the power k. This is a large non-commutative algebra. Here you have the loop homology of the CP infinity to the power m, which is just the homology of the torus, and it's a very small commutative exterior algebra, graded commutative algebra. And this map, which comes from this fibration, is like an abelianization map. So you abelianize, you make everything commute. So this huge non-commutative gadget becomes commutative. And now this loop homology of this moment-angle complex is, it's like algebra kernel. So it's like commutator subalgebra inside this non-commutative algebra. So that's like the homotopy theoretical approach. So then, yeah, that's what I said. It's commutator subalgebra. So you abelianize this non-commutative gadget and you take the kernel as a Hopf algebra. And well, you can say something about this non-commutative algebra. So to do this, you look at this kind of graph products, but now in yet another category. Now you look at the graded Lie algebra or Lie superalgebra. I mean, graded in topological sense with signs. So you look at the free graded Lie algebra on M one-dimensional generators and put the commutativity relations like in right-angle Coxeter group. So you make the square of each element is 0, but now it's a Lie square. This elements are of degree 1, so this is an untrivial relation in the graded sense, right? So this is not automatic because you have degree 1 elements. So you put these relations and you put the commutativity relation whenever you have an edge. It's called like graph product Lie algebra. So the bracket here is a graded Lie bracket with this sign. So we denoted this by L sub k. It's very similar to right-angle Coxeter groups, but you do it in the category of Lie groups. Oh, sorry, Lie algebras, graded Lie algebras. So and then, well, you can do the very same business. Simple exercise. You can write it as a colimit of graded Lie algebras when the things that you take colimit of are just trivial Lie algebras, like commutative ones. But the whole thing will become non-commutative because of the colimit. And this is similar to writing down the right-angle Coxeter group as a colimit of 0 to the power I. Okay, so now you can look at its universal enveloping algebra, and it's just the quotient of the free associative algebra, the tensor algebra, by the same relations. And this free associative algebra is what features in this description of this loop homology of the Davis-Januszkiewicz space of the CP infinity to the power k. So what you can say that there is always an injective homomorphism of Hopf algebra. This graph associative algebra, the quotient of the tensor algebra by those two sets of relations, the square is 0 and the commutator is 0 whenever you have an edge. It embeds into this graph, into this Pontryagin algebra. It always embeds as a subalgebra. And this embedding becomes an isomorphism if and only if k is flag. So if k is flag, you have the full description of this group. It has by generators and relations. And then you'll want to look at its commutator subalgebra. It's still quite complicated, even in the flag case. So now, sorry, I go back a little bit. So if you look at this exact sequence, and even if you know this one by generators and relations, like in the flag case, it's still hard to say how this looks like. And well, but if k is not flagged, then this is much larger. It contains the like Hurevich images of all higher White or higher Samuelson products. So there are much more in that than just those commutators. Right. So that's like that. That's like the homotopy theoretical side of the story. And now, so in the homotopy theoretical side of the story, you have this Pontryagin algebra, loop homology of this CP infinity to the power k. It has a subset of subalgebra, which is like this graph algebra with graph relations. And in a non-flag case, it also has this high Whitehead products. And the loop homology of Zk of the moment-angle complex is its commutator subalgebra. And now let's look at the group, at the discrete group case. In the discrete group case, you still get this homotopy fibration you start from. Then if you loop that one, then you get a short exact sequence on the level of pi1 at least. So well, this is true in general for arbitrary k, not just flag. But if k is flagged, then you just get a spherical spaces and you just get an exact sequence of pi1s of fundamental groups. If k is non-flagged, then this is still a k-pi1 space, so that will just tell you that the higher homotopy groups of those two spaces agree in the non-flat case. But let's look at the fundamental groups first. So you have this short exact sequence of groups, which just tells you that this fundamental groups of this polyhedral product is a Cartesian subgroup inside this graph product. And in the case of right-angled Artin or Coxeter groups, you just get the commutator subgroup. So this group is a commutator subgroup of this graph product. That's how I denote the commutator subgroup, by prime or dash. So, but like in the case of topological, in the case of circle or topological groups, we loop this fibration and then look at the loop homology. But here we're actually doing the same. If you loop this one, then you get just loops on a discrete group. The loop space on the classifying space of a discrete group is a group itself. So it just, if you loop this one, you just get this sequence. So it's just, you're doing the same thing as in the previous topological cases. So now you have two results. One about the homotopical situation with moment angle complex and the commutator subalgebra. That's due to Yelena Grbic, Stephen Terrio, Jivu, and myself of 2012. It tells you how to write down a minimal generator set for this commutator subalgebra. In particular, in those cases when this happens to be free, and that's quite a wide family of simplicial complexes for which ZK is a moment angle complex is a wedge of spheres, you get a minimal basis for the free associative algebra. But in general, it's just a minimal generator set. So you have like, you have one generator for every component in every full subcomplex. Well, basically, one less than connected components. You have to look at the reduced zero homology. So you look at all possible, or you look at, sorry, that K, yeah, that's a simplicial complex. Yeah, so that here you look at the all possible full subcomplexes in your K, and look how many connected components they have. And for every connected component, except for the base point, you choose some nested commutator. And that like procedure tells you how to choose it in a more or less canonical way. So that's how you get a basis in the commutator subalgebra, a minimal generator set. So that this commutators forms a basis in the submodules of indecomposable elements here. But these commutators are understood as commutators in the loop spaces of the Davis-Januszkiewicz space, right? So I mean, these commutators sit here, right? These commutators of those canonical generators here. They're not, you don't have UIs in the commutator subgroups, right? As in groups, yeah, you have like this. Sorry, yeah, I'm skipping between slides. Yeah, that's not good. Yeah, but anyway, so that's like the iterated commutators of the. So you write it as a commutator subgroup, right? So that's how you put a basis, say, in a commutator subalgebra of a free tensor algebra and so on. But in a more general setting of arbitrary simplicial complex. Okay, so that's one side, and another one is like a more recent one with Yakov Berevkin, that you can do actually the same thing for the commutator subgroup of the right-angle Coxeter groups, or you can actually do with arbitrary graph product. It's a similar description. I just put the simplest possible case, the right-angle Coxeter groups, when you have the finitely generated commutator. Otherwise, in the arbitrary graph product, it's usually not finitely generated. Like in the right-angle Artin group, you can write the similar sort of basis, but it will be infinite. So that, like the commutator subgroup, so you see that commutator subgroup of the right-angle Coxeter group, you can write it either as a pi1 of your real moment angle complex, or you can still write it down as a loop homology, although it's like, it just has H0, it doesn't have H1 and so on, because K is flagged. And yeah, I forgot, yeah, I need to say that K is flagged here still, well, because otherwise this is not true. But yeah, if you drop this one, then you don't have to say that K is flagged. So anyway, so this kind of, you still have this minimal set of generators, and with exactly same formula, but now you take group commutators. I put the round brackets instead of square. Square brackets are Lie commutators and round brackets are group commutators. So it's exactly the same formula and the same sort of procedure to picking up nested commutators. But the proofs are very different. That's kind of a drawback of our approach, that as of yet, we do not know how to translate the homotopical statement into a group theoretical statement and vice versa. I mean, you can guess, once you know a homotopy theoretical statement, you can guess how a group theoretical statement will look like, but then you need to prove it separately. At the moment, we don't have a machine, a technique to directly translate one statement to another. You have to reprove. And we are trying to develop some kind of techniques to do it simultaneously, but so far we cannot do this. So far, there are two separate sets of results which look similarly, but the proofs are very different. So anyway, and now, well, as I mentioned, sometimes this holds for arbitrary flag K, but the important case is when you actually, this commutator subalgebra or this commutator subgroup is free. Then you can actually say that this is a basis for your free group. So then there is quite a simple answer to this question, which was partially known in the group theory, probably not in homotopy theory. So it's related to what's called chordal graphs. A graph is chordal, or in other terminology, triangulated, if each of its cycles with at least 4 vertices has a chord. That means that it does not have empty cycles. So you can have like triangles, empty triangles, because there is no way to put a chord in a triangle. But whenever you have a 4 cycle, there is a diagonal in this square. And whenever you have a 5 cycle, there are 2 diagonals and so on. Therefore, it's called also like triangulated. There are no empty cycles. Such graphs are called chordal. And they feature in this optimization theory on graphs, and it was known from 60s that like these graphs are very special. They have like the vertices can be ordered in some nice way. It's called a perfect elimination order. So that like for each, they can be ordered in such a way that for each vertex, its lesser neighbors form a complete subgraph, a clique. That's an if and only if condition. And you can apply it to say something about this polyhedral products actually. So those two criterions have different powers. So absence of empty cycles and this special order are used both in this theorem. Another theorem of the 4 authors, that whenever you have a flag complexes and K is a field, then the following 3 conditions are equivalent. This remember, this loop homology of the moment angle complex is a commutator subalgebra in this loop, in the loop homology on the CP infinity to the power K, right? You always think of it as a commutator subalgebra. And if this commutator subalgebra is free, that's one condition. Another one is that ZK has a homotopy type over the wedge of spheres. That basically is this equivalence in features in homotopy theory and in its own. And that's the last one is that the one skeleton of your flag complex is a chordal graph. So you can completely classify the case when that K is a homotopy type of a wedge of spheres in the flag case, and that gives you criterion when the commutator subgroup is free. And then there is a similar statement for the graph products of discrete groups. Like this also our theorem with Berezovkin. Then again, now you look at this Cartesian, the commutator subgroup, or in more general case, it's Cartesian subgroup in your graph product, the kernel of this map, abelianization map. Sorry, not abelianization, the kernel of the map to the direct product. It's an abelianization, but all GIs are abelian. So this kernel is a free group, that's one condition. Then like this pair, this polyhedral power, as this polyhedral product is homotopy equivalent to a wedge of circles. So in the previous theorem, we had a wedge of spheres, higher dimensional sphere, and the all dimensional spheres of arbitrary dimension can appear in this wedge, but here you have just circles. And again, K1 is a chordal graph. So well, that's not a very complicated statement, but it uses both kind of approach to chordal graphs, and it uses some results on polyhedral products. So just outline how it's nice. The ideas are very simple here. So that while the 2 implies 1 is just because this is a fundamental group of this space, right? So if it's the wedge of spheres, then it's a free group. Now 3 implies 2. Then you need to use this Barry, Bendersky, Cohen, and Gittler decomposition of the polyhedral products into the wedges, and some results of Grbic and Terrio, earlier one. So yeah, actually, and then the way you use it is you use this perfect elimination order on chordal graphs. So using this perfect elimination order, you can decompose this polyhedral product and see that it becomes a wedge of spheres. So if it's a chordal graph, then you use the decomposition to show that it's a wedge of circles. Sorry. And it's the same for the previous theorem. You show in the same way that it's a wedge of spheres in the topological. And the 1 implies 3, well, that's probably the well-known argument in the group, geometric group theory. So if it's not chordal, then you have an empty cycle. For this empty cycle, you can find a subgroup in this kernel, which is a surface group. Because remember that example, when you have a chordless cycle, then the group corresponding to this chordal cycle is a surface group, and it retracts out of the whole thing. So you find a surface subgroup inside your group, so it cannot be free. So that's kind of 3 simple steps. Okay, so that's how you prove both theorems. That's simpler than to construct a basis in general. Okay, I have 3 more minutes, so I need to kind of speed up. So, well, you have these corollaries for the right angle Artin and Coxeter groups. So the commutator subgroup of the right angle Artin group is free if and only if K1 is a chordal graph, and the same for the commutator subgroup of the right angle Coxeter group. So, and yeah, as I said, that part A for the right angle Artin groups that follows from the 1981, I think, work of Servatius, Troms, and Servatius. So that's, and yeah. But the difference between those 2 things is that, like, this here, the commutator subgroup is infinitely generated, unless you have just the commutative group. And in this case, the commutator subgroup is always finitely generated, right? It's a pi1 of a finite CW complex, this real moment angle complex. Okay, so that's how you understand commutators for the right angle Artin and commutator groups and Coxeter groups. So I prepared a couple of examples. Yeah, I don't have time to go through this. That illustrates this kind of order which you use to choose a basis in your commutator subgroups that we illustrated in those theorems. So like when you have a graph like this, or simplicial complex like this, then this is a chordal, this is a tree, so it's a chordal graph. Any tree is a chordal graph. And then you have to choose that, like, for any pairs of non-adjacent vertices, you have commutators. Then you have look at the full subcomplexes on 3 vertices, and those which are connected, like 1, 2, 3, do not contribute here, and like those which have like 1, 3, and 4, the full subcomplex on 1, 3, and 4, it has 3 connected components, so it contributes 2 commutators, like 3, 4, 1, and 1, 4, 3. And the other 2 contribute 1, and now you have the whole thing has 2 connected components, so you have only 1 commutator on all 4 letters. So this commutator subgroup is free on those generators. So it's a very algorithmic way to choose a basis. And well, if you have a cycle, then you can again write down a basis in your commutator subgroup, but it's no longer free. So there is a relation on those basis elements. You can, for instance, for the boundary of a pentagon, you choose 10 elements, and there is 1 relation. But this is by no way, this is a canonical basis. So the relation will not be like the product of 5 commutators. It will be something different. But there'll be just 1 relation. So you have a 1 relator group. So whenever you start with an M cycle, you get a 1 relator group as a commutator subgroup. And then you can ask, well, the next step after being free is a 1 relator, either group or algebra. And you can ask maybe, well, we could see, yeah, that there are many examples when you get a free group, and you may guess, are there so many examples when you get 1 related groups? And that's the most recent thing that we discovered, that there are actually not so many examples of 1 relator groups among those commutators. So we have a pair of theorem. Again, this is a pair of theorem. It's not 1 theorem, because their proofs are very different, although the statements look very much the same. So one is a group theoretical one. It characterizes the case, the simplicial complex for which the commutator subgroup in the right angle Coxeter group, or you can do arbitrary graph product with a 1 relator group. And so it's basically a cycle, and you can join with a simplex. That's all you can do. And it also has a homological characterization in terms of second homology groups. And then you have also the same characterization for the algebra. So the homology is a 1 relator algebra if and only if K is just either a cycle of a join of a cycle and a simplex. And there is also homological characterization, but here you need a bigraded weighty numbers of the ZK. You cannot go with just one graded homology. So, okay, sorry for being slightly over time. Yeah, I'll stop here. And these are some references. Yeah, and yeah, I'll stop. Thank you for your attention.
Thank you. If we could all unmute and thank Taras.